Number 3. The mass of this is 6, and this angle is 65 degrees. Did not draw my angle to scale. First thing I need is the weight. It seems like all these start by asking you the weight. And the weight is mg. It's 9.8. And that's 58.8. So 58.8 newtons down. Oh, keep doing that. I know I have an eraser, I'm just not using it. Down. The vertical component of tension. So I haven't even drawn tension, but this is, let's let this be tension. And I'll resolve that into a vertical component. There's Ty. And a horizontal component, Tx. So these are all the forces acting on this thing. There's really just weight and there's tension. Tension's this way. There are no other forces. There's no air resistance or anything like that. The reason we're going to need to resolve these is because tension and weight are not in the same dimension. So trading in tension for the x and y components, and then we can do the math. Let me just write some net force equations over here. Net force in the x dimension, net force in the x dimension, net force in the y dimension, net force in the y dimension. And the first one of these is going to be m times a, which is 6 times a. All right. Then the other is going to be the sum of these vectors. So if you read the question carefully, it says it's hanging by a rope from the ceiling of a train car. It makes a constant angle with horizontal, which means as the train car moves along, this never moves up or down. There's no acceleration in the y dimension. So in the y dimension, I can use Newton's second law and say that the mass is 6 kilograms, the acceleration is 0, so the net force in the y dimension is 0 newtons. And then in the y dimension, I can also get the net force by adding up all the vectors. So this one doesn't count. There are only 2 in the y dimension. There's Ty and weight. This is positive, this is negative. So Ty minus weight, that's the net force in the y dimension. And so is this, because there's no acceleration in the y dimension. So Ty minus weight equals 0, which means Ty equals the weight. So if this is 58.8, then this is also 58.8. Except it's not. The tension in the rope, I can use trig to find this. I've got Ty, which is the opposite of this angle, and then looking for T, which is the hypotenuse. So I can use sine for that. Sine of 65 equals Ty over T, which is 58.8 newtons over T. To solve it, multiply both sides by T, divide both sides by sine of 65. And we get T equals 58.8 over sine of 65. $64.87. $64.9. The thing about this direction, tension is in both directions. So I guess I could say up and to the left, but I'm just going to say along the rope or parallel to the rope, because it's really tension is pulling in both directions. parallel to rope. Or you could just say parallel. No, parallel to rope. Horizontal component of tension, and that's Tx. Well, now that I have these two, I could use Pythagorean theorem, or I could just use tangent. I'm going to use tangent. So tangent of 65 equals Ty over Tx, which is 58.8 divided by Tx. And the same trick as last time. Multiply both sides by Tx, divide both sides by the tangent of 65. So Tx is going to be 58.8 over the tangent of 65. $27.4. And that is leftward. And finally, the acceleration. So in the y dimension, there is no acceleration. So that means any acceleration is going to be in the x dimension here. So I'll just complete what I was doing here. So in the x dimension, the mass is 6 kilograms. Multiply that by a. That gives us the net force. And in the x dimension, if we add up all the forces, that gives us the net force as well. And there is only one. There's just this. It's the only force in the x dimension. And it's negative 27.4 because it's to the left. So negative 27.4 equals 6 kilograms times A. So just need to divide by 6. Negative 4.7. Or sorry, 4.57, which means 4.57 to the left.